Okay, so good morning, good evening, good afternoon to everyone around the world. Welcome to ACM AI's Advanced Track Workshop Series. This is workshop number 3, where we're going to be talking about convolutional neural networks, or CNNs. So the link to the slides is in the anonymous feedback form linked over here. It should also be in the chat a couple of times. So if you go to this link, you'll find the feedback form plus the link to the slides. We have our GitHub here, and the attendance code is skeleton. So let's get started. So like I said, today we're going to be covering CNNs, and we're also going to review neural networks, some implementation in the Python libraries, and basically we're going to do a deep dive into CNNs. So to get started, let's try and get a sense of why we want to study CNNs in the first place. What are some of these really cool applications that make this a good topic to study? And the main application of CNNs is in computer vision. So in recent times, CNNs and computer vision have kind of become synonymous with each other. If you're saying, oh, I'm doing a computer vision task, you're like, oh, what kind of a convolution are you using? So they're very, very, very well suited for computer vision tasks, and we'll see why that is in this workshop. And I'm sure an application everyone has seen is in self-driving cars. So the stuff that Tesla and Uber and Lyft are doing, that's all based on convolutional neural networks, which is what we're going to be talking about today. And another application, if you've seen the Facebook posts where they kind of auto tag you or auto caption the image, all that's done using CNNs. Or if you go on Google Photos and you click on search, you see all these little headshots of people mapped to different images. All the image processing stuff is done using CNNs. So clearly CNNs are a powerful concept and very, very important with a wide variety of applications. So before we dive into them, let's do a quick recap into neural networks, which is kind of the stuff we covered last week. So last week, what we did is we explored the structure of fully connected dense neural networks, or we call them feed-forward neural networks. And what they essentially did is they took a vector of inputs, multiplied it with some matrices, and produced a vector of outputs. So vector, matrix, output. And it's pretty much as simple as that. And this was a really powerful structure, but as we'll see, it has its flaws. And this is kind of what our neural network used to look like. We have our input layer, which is essentially the training input data. It's just a set of vectors, each of the vectors representing a training sample. So we take a vector, pass it into a hidden layer, which is just a matrix. We multiply a vector with a matrix, apply some activation, get another vector. Multiply with a matrix, apply activation, get another vector. Multiply with the matrix, apply activation, get another layer. And as you can see, I don't know if you noticed, there's sort of a pattern here. So neural networks are essentially matrix multiplication along with some activation. And that's kind of what you should keep in mind. So once we've done that feed forward, we get some predictions, we compute some loss, we backpropagate, we calculate some gradients, and we update. Now when you start thinking about it, there are a few more steps. There's quite a lot of stuff going on in a neural network and a lot of structures flying around. Where to calculate these gradients, all these matrix implications. We need a simple way to manage all of it. And by the way, if any of this feels unfamiliar, feel free to check out our last week's workshop, which is where we discuss all this in depth. But what we want to do next is kind of show you how you would implement this really quick in Python. And I want to quickly make a disclaimer. I'm going to go through this part quickly because we're going to do a really deep dive into this at the end of the quarter. We're going to open up a Jupyter Notebook and code some of this ourselves. But just to give you a taste of what's kind of in store for the rest of the quarter, we're going to show you how we can implement a neural network using a couple of libraries. So the first one is TensorFlow. Now, a quick note about these deep learning libraries. So as you can see, there's a lot of stuff going on here, right? And a while ago, people realized that it's kind of impossible to code all of this up using NumPy arrays and for loops. So What the smart people did is they came up with these extremely high level powerful libraries like TensorFlow, Keras, and Pytorch, which kind of do all of this computation very concisely and like in a very clean and intuitive manner. So to get started, right, we have this library called TensorFlow. And what we do is we define a model as a sequential model. What does sequential mean? It means layer one, layer two, output. So there's a sequence. It's literally that simple. We define a sequential model. We add a layer with 16 neurons. We add a layer with 12 neurons. Add a layer with 10 neurons. So again, very intuitive. It's like adding a layer with 4 neurons, adding a layer with 4 neurons, and so on. Then we define our optimizer, we define our loss function, and we define some kind of a score. Don't worry about the details too much. But essentially, this 1, 2, 3, 4, 5 lines of code defines your entire neural network model. So it's very similar to like back when we did sklearn, it was just as simple. Once we've done that, we simply train our model. We give it our training data, X train, Y train, and we give it a number of iterations. There's also an extra parameter here, which is batch size. If you attended our last workshop, we covered mini batch gradient descent. And the M parameter referred to over there was in fact this batch size. Once that's done, so this line of code does all of the back propagation, the gradient descent, all the gradient computations, everything else we covered. So again, very nicely summarized in this one line of code. Once that's done, we just make our predictions. So TensorFlow is built on the back end, which is known as Keras, and it's a very simple API to use. So let me pause here for a second. Does anyone have any questions so far? Okay, I think we're good. Okay. Right. So now, so TensorFlow is a great library, right? But in this workshop series at the end of the quarter, we're actually going to be implementing stuff in another library called Pytorch. And I'm sure there's a huge debate, which is better, TensorFlow versus Pytorch, blah. We chose Pytorch. It's pretty commonly used in industry and research these days. And kind of the advantage of these libraries is that you can perform all of these calculations on your GPU very easily. So we haven't shown it here, but you can essentially take all of the stuff, store it on your GPU instead of your CPU, and that makes it much faster. So Pytorch is a little different. I think kind of the philosophy is a little different. It's a little more object-oriented, a little more modular. It results in slightly longer code, but in my opinion, at least slightly more powerful code. Oops, sorry about that. Let me put that on silent. Yeah, so what we do in Pytorch is we first define our model. So it's sort of similar to what we did here, but we're going to be defining a model over here. So we say this is a linear layer, another linear layer, and this is a Relu layer, and this is a softmax layer. Notice over here, there isn't any explicit ordering mentioned. It's sort of implicit, but no, it's not yet explicit. We just defined all these different paths, and we're going to put them together in a later step. So in the next step, we define a forward propagation function. So I think one of the things about Pytorch is that it's very close to the math. So it's called a forward propagation function. It's called a linear function. It's, we do a backward propagation function. Everything is made very explicit, very exposed, so you can go ahead and modify it as you want to. So the forward propagation function is essentially the evaluation, the stuff we covered at the beginning of last workshop. So we pass it through our first layer, pass it through Relu, pass it through our second layer, pass it through softmax, and return the value. And then like Keras, we define our model, we define an optimizer, which is cut off over here. And we define an optimizer, we define a loss function. So exactly the same. After that, we define how our training will go down. So we evaluate our model, we calculate the loss, perform backpropagation, and we perform a step. So I know I'm going through this quickly because obviously we don't have the time to cover this in depth right now. And like I mentioned again, at the end of this quarter, we're going to be going through each and every one of these steps in detail and kind of really fleshing each of them out. But that's kind of the summary of Pytorch and TensorFlow. Does anyone have any questions about these two libraries? Is the model class inheriting from another class? Yes, let me go back here. Yeah, exactly. So the model class inherits from the nn.module class, which is neural network.module class. So yeah, so it allows us to use some of the features defined inside module and makes it much easier. So yeah, like you can see, it's at least at a high level, it looks more object oriented than Keras did. Okay, any other questions? And oh yeah, one more thing. Sorry about that. I've also included the code for Pytorch kind of hidden behind this image, which I can't change for some reason. But if you go into the presentation, you'll see like there's a bit of code hidden behind the image so that if you want, you can just copy paste it and use that as your starter code. Okay. So, also we have a code snippet for mini batch gradient descent, which is the algorithm we talked about at the end of last workshop, where we essentially split our training data into a bunch of batches. And as you can see, the code is exceedingly simple. You just create a list of all your batches. And again, I'm not going to spend too much time on this because we want to really focus on CNNs, which is our main topic for today. So let's talk about the motivation for CNNs. Now, let's assume that, of course, we want to process images. What really is an image? So we can think of an image as just this matrix. You know, this is a 28 by 28 image. It has 28 rows, 28 columns, and 784 total pixels. Now, let's think about this. If we were to consider each and every one of these pixels to be a feature, we'd have an input vector of size 784. Now, that is a lot of features. Like, it's a lot of features. So if I were to define a neural network using them, let's say I have, I don't know how many are there, like 12 neurons here. The matrix would be 12 by 784. And using my calculator, let me actually see how big this is. That's 9,408 parameters in this one layer, which is a lot of parameters. And this is a 28 by 28 image. I mean, think about this. My phone camera is 45 megapixels. That's 45 million of these points. 45 million of these points in a neural network is kind of, it's not going to work, right? We don't have that kind of computation to work with that. So that kind of creates the need for a different kind of architecture, a different way to process this image. And that's where CNNs come in. So what is CNN? It's firstly, as a full form, it's a convolutional neural network. And it's a type of neural network that's well suited for computer vision. And the basic way that it works is it looks for these characteristics of images known as features. And you can sort of think of features as the ingredients that go into making an image. Like, oh, there's a curvy thing over here, there's an edge over here, a brightness variation. It's all these different characteristics or features that go into making an image. And what a CNN does is it analyzes these characteristics and derives these insights from it. And that's what we're going to be exploring in the next slides. So now let's think about what a CNN's structure is like. So far, to go back for a second, wait, here we go. Our input so far has been a vector. So it's this long linear column kind of object. But as you've seen, an image is, well, so much more than that. It's, if you kind of stretch it out like this, you kind of lose a lot of information. But an image is actually some kind of a matrix. So it has some height, it has some width, and it has some intensity value. So just looking at the matrix, we have a height, we have a width, and each value corresponds to some pixel intensity. So it's some value between 0 and 255. So 0 corresponds to black, 255 corresponds to white, and all the values in between form this grayscale image. And you can think of this third dimension, this intensity, as kind of a volume. So instead of just looking at this flat matrix, you can think of it as a volume. And if you have only one value, so this image right here is a black and white image. It's a grayscale image. So the entire grayscale spectrum can be represented using only one number, just one number between 0 and 255. But of course, in real life, we don't have just black and white images, we have colored images. And that's where RGB comes in. So instead of representing a color as just one pixel, we represent it as a tuple of 3 pixels. So we have R, G, and B. Now, what does that correspond to in our model? If we have, so let's kind of try and extrapolate from what we have here. If a black and white image is simply a matrix, an RGB image ends up being a volume. So formally, we call that a tensor. So instead of just so if you can think of it as like a 3D matrix, instead of just height and width, you have height, width, and depth. And each of those each of those different stacks, so you have one matrix, another matrix, and another matrix, each of those stacks corresponds to a different color. It corresponds to R, G, and B. So an image ends up being a height, width by 3, volume. So it ends up being a tensor. And this is kind of what the input to a CNN is. So again, to bring it back to a normal neural network, an input to a regular neural network is simply a vector. And an input to a CNN becomes a volume. And once again, this is the height, which corresponds to the height of the image, width of the image, and depth, which refers to the color channels, the RGB color channels. And this is kind of what a neural network's input looks like. So in this workshop, we're going to be covering the entire structure for CNN, which starts with the input layer, as you described it, goes on to a convolutional layer, along with activation functions. So the convolution layers are what actually extract these features and work with the features. The activation function is like Relu, tan H, pick your favorite activation function, which adds some nonlinearity. Then we do some pooling, and then pooling, which actually like reduces the dimensionality and make sure we don't completely we don't run out of memory, because there's a lot of information in images. And finally, we go to a fully connected layer, which is essentially a dense neural network, which is the stuff we covered during our last workshop as well. So this is all the stuff we're going to be doing today. And I'm going to, so this is the pipeline we're going to be covering today: input, convolution, pooling, fully connected to softmax. And we'll be walking through each of these steps today. So let me pause here. Are there any questions? This is just a high-level overview of what we're doing today. We're obviously going to be covering each of these layers in depth today. Okay, if there are no questions, let me hand it over to Adithya then.
All right, yeah, cool. All right, I hope everyone can see my screen. So we're gonna get started with talking about the layer, which is essentially where all the magic happens. This is where the model begins to understand what the picture contains and understands like what features our input images hold. So we're gonna talk about the meat of CNNs here. So let's move forward. So the way it works in CNNs, we have all our hidden neurons, and each hidden neuron in the next layer is not connected to the neuron in the previous layer. And this is what the CNN is trying to do here. Is it's trying to simulate how the real human eye works. In our eyes, each of our receptors um, do not focus on everything, all the data that comes in at a time into our eyes. Our receptors only have a sort of local receptor field, which they truly focus on and try to understand what's going on in that certain area. And CNNs are trying to do the exact same thing here. So each neuron in a hidden layer um, is really only observing a certain number of neurons from the previous layer and trying to like extract information from that layer. Um, so yeah, so this kind of gets you a good understanding of um, how this relationship between the imagery input and how the first hidden layers neurons look like. So we have all these neurons in a hidden layer, and they're all connected to um, only a certain number of neurons from the previous layer. Um, so so yeah. And as you move across the first hidden layer, you can kind of understand and see how each neuron in the hidden layer is again only looking at this 5x5 grid of neurons from the input layer. So this is like the crux of the convolutional layer. Um, where this is different from densely connected neural networks in the sense that once again you don't have that many weights connecting every neuron in the hidden layer to every neuron in the layer before that. So all right, so filters. Filters are the key to a neural network. I mean to a CNN. So what are they and what do they do? Filters in a very high level help us detect certain features in an image. So you can think of them as a volume of weights that moves across the input volume. So we discussed how um, the input CNNs receive aren't necessarily just 2x2 grids of pixels, but there's also going to be a certain amount of depth to it to represent the three different color channels, RGB. So you can think of this input image to have both a height and a width, which are the resolution of the image, as well as various pixel values, um, exactly 3 for every single pixel that represents the RGB value. Um, so yeah, so these filters, as a result of that, since these filters are moving across the input image, these filters also need to be a volume, and these filters will tend to have a smaller width and height, so that they can focus on, as we said before, a certain part of this input image. But they'll obviously need to have the same depth. The filters need to have the same depth as the input image so that once again, each filter can focus on the different RGB layers of the input image. Um, so yeah, as these filters move across the input volume, they perform this element-wise multiplications, dot product essentially, whenever it stops. So let's say the filter stops at a certain part of the input image, focusing on a certain portion of this input image. These filter values are essentially dot producted. I don't know if that's a word, but um, a dot product is taken between the filter value and the corresponding pixel value of the image. So yeah, And then what happens is the filter needs to move along across the image. The way these filters move across, or at least the number of steps it takes, is known as the stride of the filter. So a filter that only moves by 1 pixel at a time will only move with the stride of 1. But if you have filters that move across maybe by 3 pixels at a time, you will get a stride of 3. And after you perform every single dot product, the result you get is a scalar, which is essentially the new quote unquote pixel value that represents the next part of the convolution layer. But the next slide, where we show a small visualization, will make a lot more sense. So here's what's going on. We have a filter, a 3x3 filter here, represented by the orange squares. The values on the bottom right represent the filter values. And as you can see, as this filter moves across this image, this input image, which has dimensions 5 by 5, a dot product is taken between this 3x3 filter as well as the 3x3 portion of the image it's currently focusing on, and then sums up all the multiplications that are made. And that's how you get the first value in the top left corner of the convolve feature, known as the feature map, to be 4, 3, 4, and so on. And keep in mind that this example is ignoring depth, which is why we see this image as a two-dimensional matrix of pixel values, and the feature map that you get at the end, the 3x3 feature map, is also a 2D matrix. In reality, these are going to be volumes to deal with the different RGB color channels we have. But for now, we're going to keep it simple, so it's easier to visualize. All right. I'll pause here. Are there any questions regarding filters and how they work? All right. Let me see. Is the dot product shown here? So the dot product is going on like so it's not shown in the sense that what the dot product is, but if you can kind of imagine like how this 3x3 grid of the filter overlays the top left portion, for example, of the input image, you can kind of understand. So what essentially is happening is the bottom right corner of the filter, which has this x1, x0, which is essentially holding the filter value at that corresponding portion of the filter. You can think of that as being multiplied with the pixel value that it's currently on, and then summing it all up for all those 9 multiplications. When we say dot product, it's think of it just as element-wise multiplication. Yeah, so to make it simpler, we say dot products because you're essentially what you're doing is you're just multiplying corresponding values and summing them all up. But again, what is really happening here is the filter value is being multiplied with the pixel value of the input image, and then you're summing it all up for the 9 different multiplications you'll be doing because of the 9 different values you have in your filter. So yeah. So all right, so let's look at this. So here we have like a 2D input, 28 by 28 input neuron. So that means we have a 28 by 28 image. And after we apply these filters, we get a smaller feature map with dimensions 24 by 24. So there is depth to this hidden layer output. And the reason for that is we have applied 3 different filters to produce 3 different feature maps. And these feature maps are sort of stacked on top of one another to essentially create this volume. Um, so yeah. Yeah, again, just a simple visualization of what's really going on. So we at this point we can try to imagine how this filter, as it moves across the screen, begins to really like sum up all those values in that particular region and kind of squeezes them into a smaller portion um, of an image, which is why you get which is why you end up getting a smaller um, sized image, I guess you can say, when you move from the input layer to the hidden layer. So yeah, think of these filter values, as you can see back in the previous slide, essentially compressing the information stored in one part of the image into essentially like one value. So here we have 9 different pixels being squeezed into one pixel value in the feature map. And yeah, since we have 3 different three different filters, sorry, we obviously will have 3 different 3 different feature maps, which correspond to the application of each of the filters we use. So in this case, we use 3 filters. In reality, when we're actually dealing with a convolutional layer, we'll be applying a lot more features, 64, a lot more. So not just 3, we're using 3 here to kind of demonstrate a visualization of the convolutional layer. All right, so yeah, so as we discussed, a filter is a 3D volume as well. It's essentially, you can think of it as a volume of weights. These sort of connections from the filter, so essentially these filter values, these are the values that we learn during the training process of a CNN for this convolutional layer. Um, so yeah, I think I pretty much covered everything in this part of the slide. So yeah, so this window has the same depth as the input volume, as we said, because we want each of the filters to be able to deal with each of the different RGB channels that we have. So essentially, most of these filters will have a depth of 3. But again, their spatial dimensions, which is their height and the width, will be smaller because these filters, what they're trying to do really is trying to focus in on some part of the image and try to condense information from that part of the image to put it into a smaller portion of the feature map that we are getting. All right, so yeah, and a quick example. So if we have an input volume that is dimensions 28 by 28 by 10, so that means we have 10 different channels, essentially 10 different variants of each pixel value, not just 3 for RGB. Then our filter will have smaller spatial values, spatial dimensions, sorry, like 5 by 5 or 7 by 7, but the depth still has to be the same to deal with every single to deal with the depth of the input volume. All right, so discussion time. Let's just talk about some of these questions. What sort of tasks is a CNN best suited for? So as we discussed, that's going to be computer vision primarily, understanding what a picture has and dealing and like classifying pictures and videos and seeing to really understand like the features and all that sort of stuff that a picture holds. Yeah, a color image. What is the dimension of this input to a model? So as we discussed, the spatial dimensions are going to be essentially the resolution of the image, the height and the width, the number of pixels, and then usually the depth of our input is going to be 3 to represent the 3 different color channels we use for an image. And yeah, a filter is essentially how we represent and how we pick up different features inside of an image, and a stride is by how much a filter moves across an input image. Having a larger stride holds the advantage of a quicker training time, because you're moving across an image so quick that you might not pick up that you can train your model easier. But since you're moving so quick across the image, you're going to be losing out on a lot of information from the image. A smaller stride will let you focus on more of the image, but the downside there is you will be spending a lot more time in the training phase of your model. All right, so I'll stop here. Are there any questions regarding filters, strides, um, the inputs, why the dimensions of the input or the filter are as they are? Yeah, any questions before we move on? All right. So yeah. Um, so yeah, a filter scans the input volume as we discussed, and this gives us a 2D output. And so so the filter acts on a volume and outputs an area. And the reason this happens is because we're essentially doing all these multiplications, element-wise multiplication, and we're just summing it all up. And summing it all up and sticking it into one value is really just compressing all the information down, which is why we only get an area rather than a volume. So how then do we get an output volume? And that's where the application of multiple filters come in. As you're applying one filter will give you one feature map, which is the output that you get. Applying multiple features means you get multiple feature maps, and these feature maps are stacked on top of each other to essentially get this output volume. So yeah. So yeah, let's just quickly just take just kind of like wrap up what convolutional layers do. So a convolutional layer, as we discussed, consists of multiple features of the same shape. So that's important. They need to all be the same shape in a particular layer that acts on the input volume to produce the output volume. And these filter values, each you can think of them as the weights, the trainable weights of our model. And if some particular filter is looking for some feature in our input image, then you can expect the filter values at that in that filter to try to be better activated in that sense when they come across that part of the image. So let's say we have a filter that's looking for maybe a diagonal edge across um, um, when the filter comes across a part of the image that contains that diagonal edge, you'll get a much larger activation for that particular portion of the image, and that's where you get a much higher value, and that's essentially telling the model that, oh, this picture contains this particular edge and this particular feature. So yeah, and then as well for each filter, we have a bias vector, which again is important. We always need a bias value to bias our activation in a certain direction based on how we want our activation value to be. All right, so this is another really good visualization because CNNs are going to be mostly about visualization. We have this portion of the image of a mouse. Essentially, it's like a curved line. And this is the pixel representation in the middle. So obviously the pixel representations will be varied. So they're not all going to be the same value across across that part of the image. So you can see there are 50s, there are 20s, there's a 30 there, which represent the pixel values. But once you apply this filter and if you can see this filter here, the pixel representation of the filter, it only contains 30. So that means it's really looking for that particular portion of the image. That this filter is looking for this particular curved line. So when you map this filter and overlay it onto this pixel representation, you're really just doing these element-wise multiplication between all these values of 30 in the pixel representation of the filter um, with the um, with the pixel representation of the input image. And if you think about it, since all other portions of the filter image of the pixel representation of the filter are zeros, none of those um, uh, we would see a lower activation if any of the pixels in the input field in the input image um, would be higher. Um, so yeah, since this pixel representation of the input image has this particular feature that we're looking for in this filter would give a really high activation, which again tells the model that this feature that this filter represents is present in the image. All right. All right. So why do filters help? Why do we do this thing with filters? Um, so one of the biggest advantages with filters is that they reduce the total number of weights you need. Um, if you think about it, a filter only has the number of weights that is the same as the filter's dimensions. And these filters are essentially reused as you convolve across an image. These filters don't change. You just kind of slide them over this input on this input image. So the number of weights you're really using, the number of weights you're training, is small. You don't have individual weights connected to every single input neuron from the previous layer. You're just kind of focusing on a particular section, and you're reusing those that filter to move across a particular image. And then as we saw on the previous slide, filters allow detection of relationship between pixels to kind of see what sort of features are being represented. And again, that's the last point, to understand like the sort of um, the features, like diagonals, edges, patterns, whatever we need to find in a particular image. Filters help us detect those features. All right. So a few hyperparameters to keep track of. So if you guys don't remember, hyperparameters are parameters that we as the designers of a model need to tune before the training process begins. So this is unlike weights, biases, and all that stuff, which are trained during the training process. These are parameters that we need to choose beforehand before the training ever begins. So we have the number of filters, obviously, for every single convolutional layer. We want to decide the stride of filters. Again, as I said, a higher stride means you move across the image quicker. So you have less time to train. So your training time will be much faster. But as your stride increases and you move across the image at a quicker rate, you begin to lose more information from the image. And zero padding, which is what we will get to right now. All right, so zero padding. In certain cases, we want our output volume to have a certain dimension, specifically a certain spatial dimension. And zero padding helps with that. And you'll get a much better understanding when we move to the next slide. But just keep in mind that what zero padding essentially does, it pads the border of an input image with zeros or non-relevant pixel values. Since they're zeros, they're never activated. But what they do is they help us achieve a particular spatial dimension for our output volume. And this is the equation you would use in order to find what our output volume size is, or specifically the output spatial sizes, spatial volume sizes. So yeah, so this is honestly one of the best visualization you can get for a convolutional layer. So we have, as we discussed, a zero padding that goes across around the input volume. And this essentially, what this lets us do is this lets us apply the filter to every single input, every single input pixel, the pixel of the input image. And this extra padding around helps us ensure that this output volume, or at least the spatial dimension of the output volume, are 3 by 3. So as you can see, what's going on here is we have these filters. So filter W0, we have 3 different filters to deal with every single like depth, the RGB depth of the input image. So as you can see, the input image itself is split into 3 different layers to represent each of the 3 different RGB channels that you have. Again, and because of that, you have 3 different filters um, to deal with each of those RGB channels. And you have filters W0 and W1. So essentially, you're applying 2 different filters, but each filter has 3 different variants to deal with the 3 different RGB channels. And once again, as we discussed, these filters are doing an element-wise multiplication with the input volume, and then summing them up to result in these individual pixel values in our output volume. So yeah, this is essentially how a convolutional layer works. It tries to pick up on features by doing this simple element-wise multiplication to understand what sort of features and patterns the input volume contains, the input images essentially. All right, and then we'll just take a look at Imagenet. So Imagenet is a massive database of everyday images. And this picture essentially shows the filters in the first layer of a CNN that is trained with Imagenet. So in reality, the filters we've discussed are very simple. They only pick up on maybe diagonal edges or whatever, all that sort of stuff. Very simple. But in reality, we're going to see much more convoluted filters. So as you can see here, we have all these different patterns and textures that these filters are trying to pick up on. So essentially, you can see we have diagonals here, weird diagonals, and then you have these sort of like columns and bars going on. Much more convoluted features. So true, so true. Yeah, and then again, you can see we have colors as well, and these colors are used, and we have these colored filters to pick up on different colors in different parts of our image. So a lot more complex than just the sort of basic filter that we've been discussing up till now, but it gives you an idea of how these convolutional layers help pick up on different features in our image. And CNNs don't just have one convolution layer, they'll have multiple, some designed by Google and other very complex CNNs will have a lot more convolutional layers to really pick up on different features. So yeah, that's convolutional layers and how they work. Are there any questions related to everything we've discussed till now? All right. All right. If there aren't any questions, I will hand it over to Jenson to take care of our next section.
Yeah, so let's actually take like a 5-minute break. So I guess we'll come back at like 8:01. All right, I hope everyone is back. Okay, so let's talk about other layers other than the convolutional layer. So again, here's an overview of the architecture of our model. So we just passed through the convolutional layer, and now we're going into the next layer, which is Relu. Okay, oh wait, whoops. So, all right, sorry about that. So Relu is basically just a nonlinear layer. And in the next couple of slides, we're gonna go into what exactly is Relu and the significance of its shape. All right, so Relu stands for a rectified linear unit, and it looks something like this. So all we're doing in this layer is we're just applying Relu to the output of the convolutional layer that we just talked about. So essentially, if the output is positive, then we just leave it. But if the output is negative, then we'll change it to 0. Okay, so a natural question to ask at this point is, why are we choosing Relu over other activation functions that we talked about, like sigmoid? So the main reason is because the derivative of sigmoid has a relatively small range, so between 0 and 0.25. And this actually leads to an interesting problem called vanishing gradients if we're dealing with like a complex CNN model with multiple of these, I guess, with a lot of layers. So essentially, like when we're doing backpropagation, if the gradient is like a small value, like between 0 and 0.25, we're essentially multiplying a lot of these small values, small gradients together, and the result would be like a value that's very close to 0. And so when it comes time for us to update our weights, it might lead to us like not updating our weights at all, which would lead to suboptimal performances. So the way that Relu solves this problem is by having gradients values that are larger. So in this positive region here, the gradient would be 1. But in the negative region here, the gradient is 0. So this is like why Relu can quote unquote kill neurons with negative output. So I guess what I mean by that is if the output of a neuron is negative and we pass it through Relu, then Relu is just going to zero it out. Like it's just going to turn its value to 0. So what that means is it will not have a influence on the prediction that our model makes. So I guess another implication by using Relu is if the output of a neuron is negative, then its gradient is going to be 0. So what we're essentially doing during backprop is we're cutting off the channel of communication of the loss back to this neuron. So we're not going to be updating it at all. So what this creates is sparseness, which I guess is a form of regularization. So what regularization is, we're basically punishing the model for being overly complex. So this can actually help with overfitting. So yeah, there are a lot of benefits related to sparseness. So that's just one of them. Okay, before I move on, is there any questions about Relu? Okay, if not, I'm just gonna move on to our next layer here, which is max pooling. Okay, so when we apply pooling layers to our models, we generally have a few objectives in mind. So the first one is to reduce or downsample our spatial size, the spatial size of our features, both in terms of height and width. And the second objective here is to reduce the amount of parameters. So that would be weights and biases of our model, and therefore reducing the amount of computational time that we need for the training and testing phase. And yeah, applying pooling layer can also like control overfitting, I guess. It's similar to how Relu can be a form of regularization. All right, so let's talk about max pooling. So max pooling is just a form of pooling, but it's by far the most popular one. So all we're doing in this max pooling layer is we're partitioning our feature map into subsections, I guess. So in each subsection, we're going to be taking the maximum value for that section, and we'll just, so okay, let's actually go through this example. So say our feature map is 4x4, and we choose a filter size of 2 and a stride of 2. So what we're doing here is we're partitioning this feature map into 4 subsections. And so in this red portion here, the maximum is a 6. So that's why we have a 6 here. In this green section, the maximum is an 8. So we have an 8 here. And yeah, I think you guys get the idea. So yeah, just by doing this one operation, we have effectively downsampled our feature map by 75%. So that's gonna significantly reduce the amount of computation that we do for like future layers if we're having like a more complex architecture. All right, so another way to do pooling is to take the average value for each section. So this is called average pooling. This works very similarly to max pooling. So I guess instead of, so given the same parameters like the 2x2 filters and a stride of 2, so we're essentially taking the average of each subsection as opposed to the maximum. So for example, in this orange portion here, we're taking the average of 0, 0, 2, and 2, and we get 1. And similarly, in this gray section here, we're taking the average of 2, 4, 6, 8, and we get a 5. And yeah, I think you guys get the idea. So, okay, before I move on, are there any questions regarding to max pooling and average pooling? Okay, I'm gonna take that as a no, I guess. Again, like if you have any questions, feel free to type it in chat or unmute yourself. Okay, so let's talk about some common practices for pooling itself. So yeah, some common hyperparameters is the filter size, F, and the stride, which is S. So this is very similar to the hyperparameters that we discussed for the convolutional layer. So if we choose the filter size of 2 and a stride of 2, then we'll end up with disjoint subsections or partitions of our feature map, which is similar to what we saw just now. But if we choose a filter size of 3 and a stride of 2, then if you think about this visually, then this would lead to some overlapping when we're doing pooling. So this can have some interesting interplay. Okay, so well, what about padding? So do we use padding for the pooling layers? So the answer to this is it's actually pretty uncommon to use padding in the pooling layer. So if you think about this, like when we're doing padding, we're just like adding some zeros to the edges of our feature map. So for max pooling, like we're taking the maximum value in each subsection. So 0 is like almost never going to be the maximum value. So this is not gonna have that big of an effect on max pooling. And for average pooling, like this would actually like mess up the averages that you take. So kind of just dilute the features that you detect in your feature map. So this is actually not ideal. So in practice, max pooling generally outperforms other forms of pooling. And we're going to go into why that's the case in the next couple of slides. So yeah, let's go through the example to illustrate like some of the possible drawbacks for each of the pooling methods. So Okay, so let's look at the example at the top here. So this feature map is mostly white. So white here corresponds to 255. So that basically means our feature map has a high activation, and black means corresponds to 0. So that means our feature map has low activation. So, okay, so let's look at this top left corner here. So this would correspond to 0, 255, 255, and 0. So if we do max pooling, the maximum is 255. So yeah, I guess if the feature map has mostly high activation, if you do max pooling, you're gonna lose some information about, like, I guess, features of lower activations. Whereas if you do average pooling, if you take the average of these 4 values, you'll end up with 128. So what you end up after doing average pooling is you kind of get like a diluted version of your feature, whereas like for max pooling, you just completely lose the feature. Okay, that's not a question. Never mind. Okay, so, but actually let's look at this bottom example here because it's much more common for our purposes. So yeah, this feature map is mostly black. So this is mostly zeros, which is a lot more common than like mostly 255s because our features is like almost never going to be like everywhere in our image, or yeah. So after we do max pooling, if we look at this top left corner again, we take the maximum value here, which is 255, which actually works very nicely because it preserves the regions of high activations. So it preserves where our features are actually present. But when you do average pooling, we only get a 128 from this top left corner. So what average pooling does here is it actually like dilutes the feature or dilutes your feature map. And this could have like unintended consequences, like maybe this feature would not play as big of a role when it comes to like determining what the output of your model should be. So I guess one way of thinking about max pooling is it forces your model to be like very decisive. So yeah, basically if your model is like very certain that a certain feature is in your input image, then it'll output a 255 and max pooling would be able to preserve it. Whereas with average pooling, it kind of just washes that, I guess, that value away. So yeah, any questions regarding to this example? If not, we prepare some questions for you guys to discuss. So we'll actually like to open the floor for you guys. I guess I'll give you guys like a second to think about it or a minute, and feel free to like type your answer in chat. Yeah, if anything is unclear, like feel free to let us know so we can explain again. Okay, we got an answer for the first question, I believe. So what is the purpose of the pooling layer? So it's reduce the size of the input and simplify calculations. Yes, that is exactly correct. Yeah, and also control overfitting. Okay, so yeah, those are good answers. I guess for the second question, like the answer is like also this like similar, because like essentially what we're doing like in the pooling layer is we're trying to downsample our feature map while retaining like more important like information about our features. So there's obviously a trade-off here. We're trading like computational power for like information about our feature, but as long as we retain like critical information about our feature, we're okay with like losing some less important information for computational speed. So we actually included some resources here about pooling. So feel free to check that out like in your own time. All right, so yeah, we have finished covering the convolutional layer, Relu layer, and the max pooling layer. So in practice, like there's usually like multiple of these like convolutional layers and max pooling layers, which is why these are being like bracketed because they're repeated layers. But the idea is very similar, like even if you have multiple of these layers. So we're now gonna move into the fully connected layers. Okay, someone asked the question, is it like compressing an image? Yeah, you can think about it that way. But like, I guess it's not completely like compressing, because I think compressing usually like retains all the information. But what we're doing with convolutional layers and max pooling layers is we're extracting like features. And with each level, we're extracting like higher and higher level features. So in the first convolutional layer, we might be extracting some low level features like an edge or like some color gradient. But in like the second and the third convolutional layer, we might be extracting some higher level features like an ear or an eye if we're doing like face recognition. But yeah, don't quote me on that, because like I think each architecture like does things kind of differently, but the idea is like the same. Okay, so let's move on. So the intuition behind including fully connected layers in our CNN is we want to like make a prediction at the end. So for feed-forward neural networks, we used softmax. So the input to the softmax function is a vector where each element corresponds to a certain class. So remember, softmax is for multi-class classification. And the output vector is a probability that represents like how likely that particular set of features, or in this case, I guess it will be an image because we're talking about image classification. So how likely is that image corresponding to like a cat or a dog or a fish? So I guess in this example, okay, let's say the first number corresponds to a dog, then we're basically saying there's a 46% chance that this image is a dog, and like 34% this image is something else like a cat, and 20% that this image is like something else, maybe like a fish. So the problem with having convolutional layers only is they don't actually output vectors like I think Sudhanshu and Adithya discussed earlier, but instead the outputs are three-dimensional tensors. This is assuming we are doing we have multiple filters and we're doing colored images. We're dealing with color images. So we want to convert that output to a vector of probabilities, similar to what we did for feed-forward neural networks. So yeah, so that's why we're including some fully connected layers at the end. So recall, fully connected neurons have full connections to all activations in the previous layers of the neural network. So yeah, this is represented by this image, this figure here. So before we can feed the output of our convolutional layers, which is a 3D tensor, into our fully connected layers, we need to first unroll it or flatten it. The output of our previous layer, which is max pooling. So intuitively, what unrolling means here is we're kind of squishing a 3D volume into a 1D vector. So I guess the order you do this doesn't really matter. Like in practice, you're probably just gonna call some like you're gonna call like NumPy to do it for you. So this is actually kind of trivial in practice. So after we have flattened the output of the maxwelling layer, we're gonna forward propagate the flattened output through the fully connected layers, similar to what we did for the last workshop. So yeah, that's basically it. So obviously at the end, we have this softmax layer here. So we're just applying, so similar to how we apply Relu to the output of to the convolutional layer, we're applying softmax to the output of the fully connected layers, and that would correspond to a vector of probabilities. That would be our prediction. Okay, so that's pretty much it regarding to the architecture of our model. So yeah, I'm gonna pause here for a second to take some questions if there are any. How does backprop work with CNNs? That's a good question. It's actually very similar to how it worked for feed-forward neural networks. So yeah, with backprop, we're backpropagating the error through our different layers. And obviously, like the math behind backprop for CNN is a little bit more involved than the math for feed-forward neural network. But yeah, we're not gonna go into it for this workshop. But yeah, I think if you're interested, feel free to like check this out. Like, I think we've linked some resources at the end. But yeah, if that's something that you're interested in, like, feel free to, I guess, come to office hours or look it up yourself. Okay, I guess the questions in the chat is being answered. So, okay, let's do a quick review of CNNs by discussing some of the advantages of CNN over feed-forward neural networks when it comes to doing computer vision. So the first advantage for CNN is sparse connectivity. So what I mean by that is the value in the output volume of our convolutional layer is influenced by a subset of the input volume. Okay, so let's revisit this example here. So as you can see, this neuron is only influenced by the input neurons in this local receptor field, which is determined by the size of our filter. So compare this to fully connected neural networks. So if this is a fully connected neural network or feed-forward neural network, then this neuron will be connected to every neuron in this input layer. And yeah, you can see like this is not scalable as we deal with like images with higher resolution. Okay. All right, so another advantage of a CNN is the parameter sharing. So what I mean by that is the same filter is being used for, I guess, for all the neurons in the input layer. So yeah, remember, I think Adithya went through this in a lot of detail, but we're basically convolving this filter over the input volume. So we're moving this filter across the entire image here to extract a feature map. So yes, you can see this one filter is being reused for an entire image input space. So that actually saves a lot of parameters. So if we're doing, so yeah, once again, like if we're doing feed-forward neural networks, then we're gonna have a lot of weights for this one neuron. And yeah, if we increase the number of hidden neurons, then this would not be scalable at all. And the last advantage is actually like a little bit more subtle, but this is what we call equivariant representation. So what I mean by this is that if any translation in the input volume is represented by a translation in the output volume. So, okay, let's revisit this picture here. So if we have an eye in this top left corner, then, and if this filter is also, I guess, supposed to detect an eye, then in our feature map, there will be a high activation in this top left corner. But if instead our eye is moved to the top right corner, then yeah, this translation will be represented like in the feature map. So yeah, that's basically what we talked about when we're doing a convolution. So if any of this is unclear to you, feel free to come to office hours or rewatch the workshop, I guess. This will be uploaded to YouTube. Okay, any questions? I'm gonna pause for like 10 seconds for questions. So it's the depth of the input is color. Yeah, okay, yes, exactly. So, okay, so in the MNIST data set, like everything is in grayscale, so there is no depth, but yeah, in practice, when we're dealing with color images, then we have 3 color channels representing R, G, and B, so that would correspond to our depth. But remember, this is different from the depth in our feature map, because where that comes from is we're applying multiple filters to our input image, and by doing so, we're extracting like different features. So if we're doing like something like face recognition, then we might have a filter that is intended to extract or detect an eye, and we might have another filter that is intended to detect a nose. And I guess by convolving like these 2 different filters, then we'll have like a feature map that corresponds to like the feature of an eye, and another feature map that corresponds to the feature of a nose. So yeah, that's why our feature map also has depth. Okay, yeah, cool. All right, so let's recall we actually discussed the MNIST data set in our last workshop, but MNIST data set is just a large database of handwritten digits, which is very well suited for computer vision. So this is actually a very common benchmark for computer vision task. So it's commonly used to train and test image processing architectures like the CNN and I guess other more like novel architectures. So the entire database contains 60,000 training images and 10,000 test images. And researchers have actually been able to accomplish an error rate like as low as 0.23% for CNNs on this data set, which is very impressive. Because if you just like try to train like a fully connected neural network, you might get like an error rate of 2%, which is actually like pretty decent because computer vision is actually a very challenging task. So getting an error rate as low as 0.23% is like very promising. And that's why like big companies like Lyft and Uber are like trying to invest in self-driving cars because yes, CNNs are like showing like very promising results. Okay, it's actually time for discussion again. We have prepared some more questions, but these are, I guess, more generic questions. So yeah, feel free to, yeah, I'm gonna give you guys a second or a few minutes to take a look at these questions and think about them. And if you have an answer, feel free to type in chat. Okay, we actually have a question. So does zero padding manipulate the size of the input or the output? So zero padding is applied to, like, I guess it's used for convolutional layers. So if we have an image and we want to, like, sometimes we want to zero pad our input image. So that, like, yeah, so this would manipulate the size of our output, because like the input doesn't really matter in this case, because all we care about is the features that are being extracted by our convolutional layers. And I guess like another reason why we use zero padding a lot of the time is we want like every pixel in our image to like be picked out at like the frequency of, so I guess, okay, I'm not explaining this very well. So actually, let me go back. Okay. I think, okay, where is the, let's go back to this example. So like, so if you can see, we're doing like zero padding on this input volume. So like, if we're not doing zero padding, then this pixel in the top left is only being detected by the filter once. But if we're doing like zero padding, and if we decrease the stride of this filter, then yeah, we definitely will be able to pick up this pixel in the top left like multiple times. Because if you notice, like pixels in the middle are more likely to be picked up by the filter than like pixels in the corners. So yeah, this might have an interesting side effect when to our model. So yeah, we kind of want every pixel in our input space, input image, to be picked up like equally by our filter. So that's another intuition behind why we used zero padding for our convolutional layer. Okay, I hope that clear things up a little bit. Okay, zero padding is also done to ensure that the size of the output matrix is the same as that of the input. I guess it's not, yeah. So this is one way to think about it, but like, I guess the size of the output is not always that important. Okay, there's another question. So filters are used to make the input data more manageable and to look for specific features. Yes, that is exactly what filters are. So another term for filters is like feature extractors. So if when you're convolving your feature over the input space, then you're basically just trying to detect, like, I guess, where certain features are. And like intuitively, if you get like a match, your activation is going to be like a large number because you're taking the element-wise product, like Adithya discussed earlier. So you can also think of the feature map as sort of heat map for the feature that is represented by your filter. So yeah, so like a high number in your feature map basically corresponds to, like, there's a very big high likelihood that your feature is present at a certain location. Okay, Relu makes gradient adjustments bigger. Is this one of the questions? Yes. So yeah, that's, I guess, gradient adjustment. What do you mean by gradient adjustment? I think you're on the right track, but like, I guess I'm not entirely sure what you mean by that. Like the amount, yes, exactly. So yeah, especially if we have like multiple of these layers, then if you use something like sigmoid, then the gradient would be like very small, and we might even like run into problem of vanishing gradients, which would lead to us not updating our weights. So yeah, that is a huge problem. And it's actually a problem that, like, researchers spend like a lot of time like coming up with new architectures to solve. So we're gonna revisit the problem of vanishing gradients like in future workshops when we talk about recurrent neural networks. So stay tuned for that. Okay, I guess. Yeah, all the questions except for the last one is being answered. So why does max pooling generally perform better than average pooling in practice? Does anyone want to try to answer this question? Images are generally on the darker side, not super bright, so max pooling works better. So I guess you're on the right track, but when we're doing like max pooling, we're doing it on the feature map, not the input image itself. So like a high activation in this case means the feature is present at the location, and a like low activation, which is represented by black, like basically means the feature is absent. Yeah, it's totally fine. It's just, I think that example is just like misleading. But yeah, it's actually pretty uncommon that like a certain feature is like everywhere in your image. So usually like the feature that you're trying to detect is only in like certain locations, which is like usually like not very common in your entire image. So if you're trying to detect something like an edge or like a color gradient, it's only like usually present in like certain parts of your image. And what we do with max pooling is we're preserving those like high activations, whereas with average pooling, we're kind of just diluting those activations away. So we're with average pooling, we're kind of losing like important information, whereas with max pooling, we're able to retain those important information that we'll use for later stages of our model. All right, so very good. Oh, actually we prepared the answers, so feel free to check that out. Okay, I'm gonna pause for one last time for questions. So it's because different parts of the image are generally different. Yes, that's a good way to think about it. And also, if you're trying to detect a feature that is everywhere in your image, you're not, that feature is not like usually important. So if you're pick up some like background color, like that's usually not important for like what you're trying to do, which is in this case like trying to do classification. Okay. Yeah, for sure. Sudhanshu, go ahead.
Yeah, hey guys, sorry, the workshop is about to end. I wanted to quickly plug another workshop we're doing on Monday with Advanced Plus Plus, which is on fairness and machine learning. And okay, let me drop the link over here. And it's a really, really important concept since all of us are so advanced in machine learning now. We should definitely keep fairness in mind when developing our models. So definitely check this event out on Monday. And yeah, back to you, Jenson. Thanks a lot.
Yeah, actually like machine like fair ML has a big role in doing like computer vision, because like I'm sure you heard about like some face recognition class have like unequal representation in its training set. So it's doing well for like certain demographics, but not so well for other demographics because of the absence of those demographics in the training set. So it's definitely very relevant to computer vision. So I really encourage you guys to go check that out. And yeah, we've included like a lot of resources on, I guess a lot of these are like pretty heavy in math, but what we did for this workshop is we have given like a pretty high level like overview of the theories behind CNN. But if you're interested in the math, like feel free to check out like these resources. And yeah, thank you all for coming. I know this is like midterm week, so we really appreciate you guys turning up. And before you go, please fill out this feedback form and check out our Facebook group, where we'll be posting like the most updated information about our workshops.
Thank you.
Yeah, no
You're
problem.
welcome.
Thank you, guys.
Yeah, thank you all for coming.
We have office hours in Discord after this, or feel free if you have any quick questions to stick around for a bit. Oh, Jenson, you want to end the recording?